Alright, what follows is a summary of what we've explored about exponential growth functions thus far. So, for starters, we're just going to start with where we began, which was we have bacteria that are doubling every 15 minutes. Now we started with 5 bacteria, and we allowed them to multiply every 15 minutes. And so we learned that after 8 15-minute periods, or 2 hours, there were 1,280 bacteria when we started with 5. And when we plot these on a graph, even by the time I get to x equals 8, you can see we started from relatively insignificant growth to suddenly very rapid growth in a short period of time. So, for example, we were going at 18 3/4 bacteria for every 15 minutes during the first hour, using average rate of change calculations, and on average we were growing 300 bacteria for every 15 minutes during the second hour, as represented by the slopes of these two chords or lines. So, the bacteria is clearly increasing at an increasing rate. So then what the other question in part one was about is a comparison against a function that we've already seen before. Um, I used 5 because we're starting with 5 bacteria, but then I remember x squared functions increasing at an increasing rate. And sometimes the 5 times x squared function matches my bacteria function, where when x is 2, y equals 20, and when x is 4, y equals 80. But everywhere else, we're going to see some relative moderate differences in the beginning, followed by extreme differences by the time x gets to 9. By the time x gets to 9, we're talking about 405 bacteria in a power function like y equals 5x squared, and we're over 6 times that much by the time we get to 9 if we're using our bacteria function. So how the bacteria population doubling lays out is, if you look at an increase of 15-minute periods, we're going to take the previous amount of bacteria, 5 times 2 in this case, and double that. So it's 5 times 2 times 2, or just 5 times 2 squared. Another 15 minutes later means one more double, which means we are talking about 2 to the third power. In other words, we take 5, double it 3 times. Here we take 5 and double it 4 times after the 4th stage. So it follows that if we do x stages, that means we're going to take the 5 bacteria, double that population x number of times. So that generates an equation for population growth that we would then be able to put into a calculator and graph it like this one. In the process, I observe that my comparison with y equals 5x squared, the exponential function does not have symmetry, and it starts off practically horizontal and then ends up practically vertical. It's a very dramatic function. And that's what we're going to explore with the remaining questions. Number 2, we were supposed to examine what if there were 4 bacteria in the dish. And I made a comparison table and I looked at the graphs, and what I see here essentially is that the behavior of the exponential function is the same. The lack of symmetry, the horizontal nature, suddenly a rapid turn upwards. We can see that after 2 hours, there's a difference of 200 or so bacteria when we started with 5 compared to when we started with 4, and there's a difference of about 4,000 bacteria by the time we get to 3 hours away. So that seems relatively significant, but I want to compare it with something a little later. First of all, observe the function in whatever this orange color is. That function is going to be the one that changes, and it's going to be in comparison to a purple function, which is 5 times 2 to the x. So here's your bacteria function. If I increase the a value or decrease the a value, we're going to see what kind of effect that has on the function. So for example, we went from 5 bacteria to 4 bacteria, and we can see the kind of effect it has on the graph. The orange bacteria, or the orange graph, is a little bit lower. Now, if I zoom out, I'm going to see that the difference is not that significant over a long enough timeline. And in fact, I can see that on this table. When I have y equals 4 times 2 to the x, I can see the differences between 4 times 2 to the x and 5 times 2 to the x is relatively insignificant. Here, by the time x gets to 50, both of these values are still a magnitude of 10 to the 15 power. So the numbers get equally large, equally fast, so to speak, even if I make small changes to my A values. So here again, if I make A values really large, you can see it has an effect on the graph, but it does not have a significant impact on the general behavior of the function. It still has mostly the same kind of stuff happening. Zoom back in, put A back to 5, and we'll study what happens to the B values in a moment. But first, we finish up the questioning. When we talk about 4 bacteria, that changes the equation to y equals 4 times 2 to the x, and it has an effect of vertically compressing our graph, but it does not change the general shape and behavior of the function. Just to make sure we know how to use these function equations, this is the same as everything we've done with functions before. I'll give you an x value or a y value, and you see if you can solve. So for example, how many bacteria after 3 hours? That represents 4 15-minute periods per hour, or 12 15-minute periods. So I want to do f of 12 equals 4 times 2 to the 12th, or 12 doubling periods, 16,384 bacteria after 3 hours. After 4.5 hours, that's 18 15-minute periods, or about a billion bacteria after 4.5 hours. So how long will it take to have a billion bacteria? Well, the answer had better be just under 4.5. Or I'm sorry, this is a million, not a billion. So then we get to part B, and it says how long till we have 1 billion bacteria. That's one with 9 zeros on it. This is essentially the equation that we're trying to solve. You could try dividing by 4, but then how do you get the x out? I'm not sure I know how to do that yet. I mean, I do, but we haven't covered that yet. But I can use intersection. So I enter 4 times 2 to the x and 1 billion, and I set an appropriate viewing window so I can see the graph. Notice again, nothing seems to happen, and then suddenly everything happens all at once. And by the time x equals 27, we get 1 billion. So we can say after 28 doubling periods, that's about 7 hours, there will be more than a billion bacteria. So after 4.5 hours, we have a million bacteria. After 7 hours, only an hour and a half later, or 2.5 hours later, then we get to a billion. Okay, so the other question was asked, what if we talked about having a nickel as our paycheck, and then we triple that every day we work? And so if I look at what I've learned so far, we have a starting value, 5 bacteria, or 4 bacteria, in this case 5 cents, a nickel, and then we have a multiplication or a growth factor, 2 for doubling, 4 for quadrupling, 3 for tripling. So now I'm going to change the b value and see what that does to my function. So the questions that were asked were how long we have to work for your pay to exceed a million. So I set y equal to a million. I look for the intersection. It says all we have to do is work 15 days. That's just over 2 weeks, or on the 16th day, our pay for that one day will exceed $1 million. If I worked for 10 weeks, that's 70 days total. This number right here is 125 with this many zeros. That's how much money you would have on the 10th week of working this job. So clearly, if you triple something repeatedly, it's going to have a profound impact in a not a very long period of time. That was also observed in our rice problem. In the rice problem, we took 1 grain of rice and quadrupled it. And so just to look at the difference between tripling a nickel or quadrupling a grain of rice, essentially what I'm looking at here is the change in our b values. What kind of effect does a change of b values have on an exponential growth function? So instead of changing the a value, we're going to keep a at 5, and look what happens when we increase our b values. It's not a vertical stretch all around. It seems to be more of a horizontal compression. And I can see that just a small change in B causes a very dramatic shift in the nature of the curve. And in fact, if I go all the way up, it almost looks vertical right away. Even if I zoom out, we can see that there's still a considerable difference in the nature of the graphs. Now look what happens when I decrease my B value until it becomes 1.24, and now it's 1. So when I change the a value, I'll put this back to 2. When I change the a value, Not very much change in the curve. And if I change the b value, there's a much more profound impact in the curve. To really drive this point home, I'm going to change the b value to 3 and make a comparison. If we change from doubling, which is this function here, to tripling, then we have an order of magnitude of 10 to the ninth power difference here between these two. So it's a significant difference. And if I change my b value to 4, the difference is even more profound. We're talking about a difference between, for some reason this isn't working. Oh, there we go. A difference of 10 to the 15th power. So it's way, way, way more dramatic when you change the b value instead of changing the a value. So that's generally what these questions are trying to get us to look at is functions in the form of f of x equals a times b to the x, and what happens when we change the a values and what happens when we change the b values. Just one quick wrap up. We look at the rice problem. It was taking 1 grain of rice, quadrupling it for every white square. We end up with 18 billion grains of rice on the 32nd square. What I've done is I've actually made some conversions using the idea that we can convert cubic inches to ounces and ounces into packages of rice for $4 a package, and what could you buy with that kind of money? So first I took the weight and turned everything into kilograms, and so there were 25 milligrams per grain of rice, and I got turned milligrams into kilograms, which is 1,000,000 milligrams, so that just reduces the magnitude of that number. And then I wanted to figure out how many freight trains that would be. I went online, I found out that the mass of a freight train, 9.898 times 10 to the 6th power. So how many freight trains would be required to hold all the rice on the 32nd square? Turns out we need to have 46 million freight trains in order to carry all that stuff. That's still a pretty big number. So then I went and found on that same website the mass of Mount Rainier, one of the largest mountains in the United States, if not the largest, I can't remember. But apparently it's 1.23 times 10 to the 15 kilograms in mass. And if you look at Mount Rainier, you'll see very, very large mountain. Our conversion asks for 0.37 Mount Rainiers, so we can actually say if you take this entire mountain and chop it right about there and take all this stuff right here, that'd be the amount of rice on the 32nd square. So that's a number that I can comprehend. At least I know it's as big as a mountain. Looking at that website in more detail, the moon, our moon, is larger than the amount of rice on the 32nd square. So we could argue that all the rice on the 32nd square could be safely held as a moon. That's just a little bit of rice. I took the number and converted it even further into dollars, and I got 2 times 10 to the 18 dollars, which was still too big for me to comprehend. And so I converted that into the gross domestic product of the United States, which gross domestic product was $15.6 trillion in 2012. The gross domestic product is defined as the value of all goods and services produced within a country in a year. So in 1 year in the United States, all the money spent by consumers, by the government, by businesses, and all the money that we made on exports after we subtracted imports, all the money that's changed hands in a year is $1.56 trillion dollars. And the amount of rice required to buy, or the amount of money required to buy all the rice on the 32nd square would equate to 182,000 US GDP. So in other words, we would have to spend all the money that we spent as a nation in 2012, 182,000 more years in order to make the money for the 32nd square. That's exponential growth. So one thing to walk away with is understanding the form y equals a times b to the x, and also I'm trying to find something here. Yeah, a times b to the x. Knowing what the a value means, knowing what the b value means, but more importantly, this idea that exponential growth shows moderate growth at first and then extremely rapid growth. It is slightly affected by changing the a value or what you start with, but is much more dramatically affected by changing the b value or the growth factor in this case. Thanks for watching.